Okay, so firstly, just to conclude this discussion about epics, we're saying that f is epic if and only if the identity of b is contained in this extension here, this extension being the load of y, such that there exists an x such that y is fx. So, I mean, yeah, like point-wise, we could say for every point y of b, there exists an x such that y is fx. But, you know, we've shown that that's equivalent to saying that tb equals exists of a of phi bar, where phi is delta b p1 comma fp2, and that holds precisely when for every point little b of b, we have that the restriction of phi, well, we have that phi of b blank sends something to true. So the interpretation of that then is that delta of b exclamation mark a comma f, which is an arrow from a to omega, has to send some a to true, okay? Which is equivalent to saying that, you know, there exists a member of a such that fa equals b. All right, so that's good. Now let's go on to understanding this. So Goldblatt claims, McClarty claims that this formula here, for all w in omega, we have that for all x in a, we have that phi implies w, that this is equivalent to saying that there exists an a such that phi. So I wanted to go through this and make sure it makes sense. I mean, we can do a quick kind of justification for this formula, in the sense that for each w, well, I mean, what we want for this to be true is that for each w, we want that if this is false, then w is false. The only thing we don't want to happen in order for this formula to be true, we don't want this to be true while w is false. Because if this is true and w is false, that means we're going to have true implies false, which is wrong. But anything else is fine. True implies true. False implies true. And false implies false all work, but true implies false doesn't work, because basically the meaning of this arrow is that this is at least as true as this. Okay, but we'll see this all more clearly. So basically, the situation we have to have is that when this stuff is false, we also want w to be false. Well, let's see this work more clearly, okay? So we're just going to start sort of from the inside out to understand what the bits mean. So for any pair arrow alpha beta into A times omega, we're going to have this pair alpha comma beta is going to be in this extension here. So of a load of x in A and w in omega, such that phi of x implies w. So we're just going to assume that phi just depends on x for this. We could go through this argument again and suppose that phi maybe depends on x and y, where y is in B, but we won't bother, not now. So anyway, this happens if and only if doing the interpretation of this on alpha comma beta gives true. So that would be the interpretation of phi x implies w with three variables x and w. We work out what this is. It is phi of p1 comma p2 of alpha comma beta and we want implies of phi of p1 comma p2 of alpha comma beta to be true, and then this is happening if and only if, just taking these alphas and betas inside, if and only if we have phi of alpha comma beta is true. Now what's this implies arrow mean? Well, it's a classifying arrow of less than or equal to, so this happens if and only if chi of less than or equal to of phi of alpha comma beta is true, and this happens if and only if phi of alpha comma beta is in less than or equal to, which means precisely that phi of alpha equals phi of alpha and beta. So if you think about it, this is fine when phi of alpha is true and then beta is true, true and true is true. If this is true, if phi of alpha is true and beta is false, then true and false is false, but this is true, so that goes wrong. The other cases work, okay? Ft gives a f and t is f, but that is f, so that's fine. And f is f, which is f over there, so that's fine. So the only case we have to avoid in order for this to work is that phi of alpha is true and beta is false. So basically I'm saying that this happens, and we're talking about in set, of course. Things are more complicated when we have more truth values and so on, but in sets this happens if and only if when beta is false, we must have that phi of alpha is false. Well, fine, okay, so let's carry on. We'll set h is equal to the terminal object, and we want to now interpret a bit bigger part of this expression. So for a point beta of omega, we're going to have that beta's in this extension here, the load of w in omega, such that for all x in A, phi of x implies w, or beta is going to be in that if and only if the interpretation of for all x in A of phi of x implies w acting on beta gives true. So it comes down to interpreting this thing with a for all in it, and so the interpretation of this is going to be for all A, interpretation of phi of x dash implies w transposed acting on beta has to give true. So let's call this stuff let's call, so basically we're going to define theta here to be equal to the interpretation of phi of x dash implies w over w and x dash. So basically theta is this thing in here. So then this statement becomes for all a theta transpose of beta is true. And again, we can use our previous understanding of how exponential objects work. So this is going to be true. I mean, basically, theta transpose of beta is going to be a point of omega to the power of a, and doing a for all on that is going to give a true if this point of omega to the power of a corresponds to a full subobject. More precisely, if it's the name of a classifying arrow from a to omega that is basically a true arrow, okay? So more precise, and what is theta transpose beta the name of? Well, it's the name of theta of beta comma blank, which is theta of beta exclamation mark a comma 1a. So basically this is going to happen, this for all stuff, for all theta bar beta is true. That's going to be the case if and only if theta of beta comma blank equals TA, which is true after exclamation mark a. But what is this theta of beta comma blank? Well, just calculating it out, we find it's implies of theta of 1a comma beta of exclamation mark a. So basically we're seeing if theta with this variable, depending on stuff on in a, always implies this true value beta. And so let's see when this will be the constantly true arrow. Well, if beta is true, we've got no problem because it's the case that whatever theta is, it will imply true. Okay, because false implies true and true implies true. So that's fine. So when beta is true, this is automatically the constantly true arrow. But on the other hand, if beta is false, then the only way that theta of b comma blank will be true is if whatever a we feed in, we always get phi of a is false. So in other words, if phi of a is false for each a. So in conclusion, we've got that the interpretation of for all a of phi of x implies w over w acting on beta gives true if and only if for all a transpose of theta acting on beta gives true if and only if when beta is false we have to have that phi of A is false for each A. And we'll come back to that later. But now we've kind of built up and we can now tackle the big formula. So basically now what we want to understand is, when is this going to be true? That for all W, we have that for all X, phi implies W implies W. So basically, because I don't have any free variables left, when we do the interpretation of this, it has no free variables. At this point, I was sort of regretting not putting an extra dependency of phi on something else. But, that's fine. We can still make do. But, the point is, when is the interpretation of this true? Okay. When does it correspond to the true arrow? Well, we can give the interpretation of this, and it's going to be for all omega. We have mu bar, where mu is the interpretation of this stuff here inside the brackets, which is for all x, phi of x implies w dash, and we want the interpretation of that over w dash, but we'll also put an exclamation mark here because we need our arrows to match up. I mean, here like basically we want like this. Mu bar is a point of omega to the power of omega, so we want mu to be a point from 1 times omega to omega, so an arrow from 1 times omega to omega, and that's why we put this extra exclamation mark here to denote that there is constant stuff, although that doesn't really factor into the issue. Anyway, the point is that we're going to have, like, this is just a mu bar is just a point, and it's going to be true that for all omega we've got mu bar gives true if and only if mu bar, this point of omega to the power of omega, corresponds to a full subobject. More precisely, when we get the arrow mu bar underscore, which is equal to mu of exclamation mark omega comma 1 omega, when this, the thing that omega bar is the name of, is the sort of constantly true arrow. Okay, so it's equal to t omega. So that's what we need to check then in order for this to work. Now, I'm basically, when we're dealing with the interpretation, I want to call this stuff V, okay? More precisely, V of W dash is the interpretation of this stuff here, which is the first part. And the way this works, excuse me a second. Yeah, so basically, the this V here, I probably shouldn't say V of W dash here, because I suppose the W dash evaporates, but this is the, so maybe I ought to cross off this bit, but V is my shorthand for the interpretation of this part of the term that we're trying to find the interpretation of. And so V is the interpretation of for all x, phi of x implies W dash. And, well, actually, no, I'm calling, yeah. And the way that this works, basically, when it's given an input W dash, is it's going to give us false when the input W dash is false, and when phi of A is true for some A, and it's going to give us a true otherwise. And that's basically because of the reasoning that I've already gone through. So, I mean, basically this V stuff is, where is it now? I mean, basically this here, I mean, we could call this stuff V of beta. And we see that the only way that this can be false is if beta is false and there exists a such that phi of A is true. So anyway, now we can go back to interpreting our whole formula. So, like I say, basically the interpretation of this long thing is going to be true if and only if we've got that mu after exclamation mark omega comma 1 omega is true omega. And so now let's work out what this thing is, this thing that mu bar is the name of. So firstly, what's mu? Well, mu is, doing the interpretation, it's implies arrow of for all x, phi implies w dash, comma w dash, but we do interpretations of that. So it becomes v of p2, comma p2. So that's what mu is, but we're really after mu after exclamation mark omega, comma 1 omega, so we can get this mu bar under square brackets thing, which is the thing that mu bar is the name of. And so when we do this and work it out, we find that this thing that mu bar is the name of implies v comma 1 omega. And we know how v works, okay? So as a summary then, we've got that this entire big statement, which we're claiming is equivalent to saying that there exists an x such that phi, that this is true, if and only if the thing that mu bar is the name of is true omega, and that's going to happen if and only if we don't have that this part here is false while this part here is true. In other words, if and only if when this part here is false, sorry, the only case we don't want is that this part here is true and this part here is false. So in other words, what we need is that when this is false, we have to have that this part here is also false. Now, what this here is, it's the input of v. So what we need in order for this stuff to work is that we need v of false to be false. Okay, because when this is false on the right, we have to have that this thing on the left is also false. And this thing on the left is v of this thing on the right. Okay, so what we need is that v of false is equal to false. And if we look again at the definition of v, we see that this is the case. The only way, when w dash is false, v of w dash will give false if and only if there exists an a such that phi of a is true. And that's exactly what we need, because that's the interpretation we're hoping that this formula would have.